Determining the value proposition is the first step. Highlight the electrician's experience and expertise in commercial construction because this translates to a higher level of knowledge and problem-solving skills, especially when dealing with residential service work. Emphasize his attention to detail, his commitment to quality, and his personalized service that he offers. Then you want to benchmark against competitors. Research indicates that similar businesses charge from $68 to $75 per hour, or a trip charge in addition. Consider these rates as a starting point for pricing strategy. Next, perform a cost analysis. Calculate all the expenses, including vehicle costs, insurance costs, material expenses, and overhead costs. Determine the hourly rate necessary to cover all these costs and provide a reasonable profit margin. Once you know the expenses, define a pricing structure. Consider a tiered pricing structure. This means offering a low base hourly rate for routine tasks and a higher rate for complex or specialized jobs. Offer package deals for multiple services or extended contracts to incentivize customers, and implement a service charge or a trip charge if necessary to cover costs associated with travel and setup. Then, do some targeted marketing. Identify the target audience of homeowners who value quality and experience. Develop marketing materials that highlight the unique strengths and value proposition. Network with real estate agents and homeowners associations to promote the services. In terms of negotiation strategies, be confident in the pricing and explain the value that is provided. Be willing to negotiate on the total cost while maintaining the hourly rate, and offer discounts for repeat customers or referrals. In addition, consider offering a free consultation to potential customers to assess their needs and build rapport. Encourage customer testimonials and reviews to build credibility. Stay up to date with industry trends and technologies to demonstrate the commitment to providing exceptional service. Seek professional advice from a certified public accountant to ensure the pricing strategy aligns with financial goals. When it comes to electrical work, safety is paramount. Therefore, you must strictly adhere to all relevant safety regulations and codes, such as those outlined in the National Electrical Code, or NEC. Familiarize yourself with the latest edition of the NEC and any local amendments that may apply in the specific jurisdiction. It is essential to have a thorough understanding of the code requirements for wiring methods, overcurrent protection, grounding, and other critical aspects of electrical installations. Prior to commencing any electrical work, always perform a comprehensive risk assessment to identify potential hazards and implement appropriate safety measures. This includes wearing personal protective equipment such as safety glasses, gloves, and appropriate footwear. Use insulated tools to minimize the risk of electric shock and ensure that all equipment is properly grounded. Never work on live circuits unless absolutely necessary, and always follow lockout-tagout procedures to de-energize circuits before beginning any work. When working with electrical panels and equipment, maintain a safe working distance and avoid contact with energized components. Use a voltage tester to verify that circuits are de-energized before touching any wires or terminals. Be aware of the potential for arc flash and wear appropriate arc-rated clothing and face protection when working on energized equipment. Proper grounding is essential for electrical safety. Ensure that all electrical systems are properly grounded to provide a path for fault current to flow back to the source, tripping the overcurrent protective device and preventing an electrical shock. Use appropriate grounding electrodes, such as ground rods or metal water pipes, and connect them to the electrical system with grounding conductors of the correct size. Inspect grounding connections regularly to ensure that they are secure and free from corrosion. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect electrical circuits from overloads and short circuits. Select overcurrent protection devices with the appropriate ampacity and interrupting rating for the circuits they protect. Never bypass or disable overcurrent protection devices, as this can create a serious fire hazard. Regularly inspect overcurrent protection devices to ensure that they are functioning properly and replace any that are damaged or defective. Wiring methods play a critical role in electrical safety. Use the correct type and size of wiring for the intended application and install wiring in accordance with the NEC and local codes. Protect wiring from physical damage by using conduit, cable trays, or other appropriate methods. Avoid running wiring through areas where it may be exposed to moisture, chemicals, or extreme temperatures. Make sure all electrical connections are tight and secure to prevent loose connections, which can cause overheating and fires. Use approved connectors and terminals for all wiring connections, and never use wire nuts to connect different sizes or types of wires. Follow proper wiring practices to ensure that electrical circuits are safe and reliable. Electrical equipment must be properly maintained to ensure its safe and reliable operation. Regularly inspect electrical equipment for signs of damage, wear, or corrosion. Clean electrical equipment to remove dust, dirt, and debris, which can cause overheating and insulation breakdown. Lubricate moving parts as needed to prevent friction and wear. Repair or replace any damaged or defective electrical equipment promptly to prevent electrical hazards. Follow manufacturers' recommendations for maintenance and servicing of electrical equipment. Working with electricity can be dangerous, so it's important to be aware of the hazards and take steps to protect yourself and others. Electrical shock can occur when a person comes into contact with an energized electrical circuit. The severity of an electrical shock depends on the voltage, current, and duration of contact. Electrical shock can cause burns, muscle contractions, cardiac arrest, and even death. Arc flash is a dangerous electrical explosion that can occur when there is a short circuit or insulation failure in electrical equipment. Arc flash can produce intense heat pressure and light, causing severe burns and other injuries. Electrical fires can occur when electrical equipment overheats, short circuits, or malfunctions. Electrical fires can spread quickly and are difficult to extinguish, posing a serious threat to life and property. Electrical hazards can be prevented by following safe work practices and using appropriate safety equipment. Always de-energize electrical circuits before working on them, and use lockout-tagout procedures to prevent accidental energization. Wear personal protective equipment such as safety glasses, gloves, and insulated footwear. Use insulated tools to minimize the risk of electric shock. Maintain a safe working distance from energized equipment and be aware of the potential for arc flash. Regularly inspect electrical equipment for signs of damage or wear and repair or replace any defective equipment promptly. Never bypass or disable safety devices such as circuit breakers and ground fault circuit interrupters, or GFCIs. By following these safety tips, one can help prevent electrical hazards and ensure a safe working environment. Understanding the National Electrical Code, or NEC, is crucial for safe electrical installations. The NEC is a comprehensive set of standards and guidelines for electrical wiring, equipment, and installations. It is updated every 3 years to reflect the latest advancements in technology and safety practices. The NEC covers a wide range of topics, including wiring methods, overcurrent protection, grounding, equipment installation, and special occupancies. It provides detailed requirements for electrical installations in residential, commercial, and industrial buildings. The NEC is adopted by many states and local jurisdictions, and it serves as the basis for electrical inspections and code enforcement. Compliance with the NEC is essential for ensuring the safety and reliability of electrical systems. The NEC is organized into chapters, articles, and sections, making it easy to find specific requirements for different types of electrical installations. Chapter 1 covers general requirements, such as definitions, scope, and administration. Chapters 2 through 7 cover specific requirements for wiring and protection, wiring methods and materials, equipment for general use, special occupancies, special equipment, and special conditions. Chapter 8 covers communication systems, and Chapter 9 contains tables and examples for calculating electrical loads and conductor sizes. Some key articles in the NEC include Article 110, which covers requirements for electrical installations, Article 210, which covers branch circuits, Article 220, which covers branch circuit, feeder, and service calculations, Article 230, which covers services, Article 250, which covers grounding and bonding, Article 300, which covers wiring methods, Article 310, which covers conductors for general wiring, Article 400, which covers flexible cords and cables, Article 430, which covers motors, motor circuits, and controllers, Article 440, which covers air conditioning and refrigeration equipment, Article 500, which covers hazardous locations, Article 517, which covers healthcare facilities, Article 547, which covers agricultural buildings, Article 600, which covers electric signs and outline lighting, Article 625, which covers electric vehicle charging systems, Article 680, which covers swimming pools, fountains, and similar installations, Article 690, which covers solar photovoltaic systems, Article 700, which covers emergency systems, Article 701, which covers legally required standby systems, and Article 702, which covers optional standby systems. To effectively use the NEC, it is important to understand the organization and structure of the code. Start by identifying the type of electrical installation you are working on and then locate the relevant articles and sections in the NEC. Read the code requirements carefully and make sure you understand them before proceeding with the installation. Use the tables and examples in Chapter 9 to calculate electrical loads and conductor sizes. Consult with a qualified electrical inspector or engineer if you have any questions or need clarification on the code requirements. Regularly review the NEC to stay up to date with the latest changes and revisions. Understanding the NEC is essential for safe and compliant electrical installations. Proper grounding and bonding are critical for electrical safety. Grounding provides a path for fault current to flow back to the source, tripping the overcurrent protective device and preventing electrical shock. Bonding connects all metal parts of an electrical system together to create a low impedance path for fault current. The NEC requires that all electrical systems be properly grounded and bonded to ensure the safety of people and equipment. Grounding electrodes are used to connect the electrical system to the earth. Common types of grounding electrodes include ground rods, metal water pipes, and concrete encased electrodes. Ground rods are typically driven into the earth at least 8 feet deep and spaced at least 6 feet apart. Metal water pipes can be used as grounding electrodes if they are in direct contact with the earth for at least 10 feet. Concrete encased electrodes, also known as UFA grounds, are installed in the concrete foundation of a building. Grounding conductors are used to connect the grounding electrode to the electrical system. Grounding conductors must be sized according to the NEC and must be made of copper or other approved material. Equipment grounding conductors, or EGs, are used to connect the metal parts of electrical equipment to the grounding system. EGs provide a path for fault current to flow back to the source, tripping the overcurrent protective device. Bonding jumpers are used to connect different metal parts of an electrical system together. Bonding jumpers ensure that all metal parts are at the same electrical potential, reducing the risk of electrical shock. The NEC provides detailed requirements for grounding and bonding electrical systems. Article 250 of the NEC covers grounding and bonding requirements for electrical systems. It specifies the types of grounding electrodes that are permitted, the size of grounding conductors, and the methods for bonding metal parts of electrical systems. It is important to follow the NEC requirements for grounding and bonding to ensure the safety of people and equipment. Ground fault circuit interrupters, or GFCIs, are life-saving devices that protect people from electrical shock. GFCIs monitor the current flowing in a circuit and quickly interrupt the power if a ground fault is detected. A ground fault occurs when current flows through an unintended path, such as through a person's body. GFCIs are required in areas where there is a high risk of electrical shock, such as bathrooms, kitchens, and outdoor locations. GFCIs work by comparing the current flowing in a hot and neutral conductors of a circuit. If there is a difference of more than 5 mA, the GFCI trips and interrupts the power. GFCIs can trip in as little as 1/40th of a second, which is fast enough to prevent serious injury from electrical shock. There are two main types of GFCIs: receptacle type GFCIs and circuit breaker type GFCIs. Receptacle type GFCIs are installed in place of standard electrical outlets and provide ground fault protection for that outlet and any outlets downstream. Circuit breaker type GFCIs are installed in the electrical panel and provide ground fault protection for an entire circuit. GFCIs should be tested monthly to ensure that they are functioning properly. To test a GFCI, press the test button on the device. The GFCI should trip and interrupt the power. To reset the GFCI, press the reset button. GFCIs are an essential part of electrical safety and should be installed in all areas where there is a high risk of electrical shock. Arc fault circuit interrupters, or FCIs, are devices that protect against electrical fires caused by arc faults. Arc faults occur when there is an unintentional electrical discharge between two or more conductors. Arc faults can generate high temperatures that can ignite nearby combustible materials, leading to a fire. FCIs are designed to detect arc faults and quickly interrupt the power, preventing a fire. FCIs work by monitoring the current flowing in a circuit and detecting abnormal patterns that indicate an arc fault. When an arc fault is detected, the FCI trips and interrupts the power. FCIs are required in many areas of the home, including bedrooms, living rooms, and dining rooms. The NEC requires FCIs to be installed in all 120-volt single-phase branch circuits supplying outlets or devices installed in dwelling units. There are two main types of FCIs: branch circuit FCIs and outlet branch circuit FCIs. Branch circuit FCIs are installed in the electrical panel and provide arc fault protection for an entire branch circuit. Outlet branch circuit FCIs are installed at the first outlet on a branch circuit and provide arc fault protection for that outlet and any outlets downstream. FCIs should be tested monthly to ensure that they are functioning properly. To test an FCI, press the test button on the device. The FCI should trip and interrupt the power. To reset the FCI, press the reset button. FCIs are an important part of electrical safety and should be installed in all areas where they are required by code. Surge protection devices, or SPDs, protect electrical equipment from voltage surges. Voltage surges are temporary increases in voltage that can damage or destroy electronic equipment. Voltage surges can be caused by lightning strikes, power grid switching, or other electrical disturbances. SPD work by diverting excess voltage away from sensitive electronic equipment. When a voltage surge occurs, the SPD clamps the voltage to a safe level, protecting the equipment from damage. There are three main types of SPD: Type 1 SPD, Type 2 SPD, and Type 3 SPD. Type 1 SPD are installed at the service entrance of a building and provide protection against external voltage surges, such as those caused by lightning strikes. Type 2 SPD are installed at the electrical panel and provide protection against internal voltage surges, such as those caused by power grid switching. Type 3 SPD are installed at the point of use, such as at an electrical outlet, and provide protection against local voltage surges. SPD are rated by the surge current capacity, which is the amount of current they can safely divert. The higher the surge current capacity, the better the protection. SPD should be installed in accordance with the manufacturer's instructions and the NEC. SPD are an important part of electrical safety and should be installed to protect sensitive electronic equipment from voltage surges. Proper wiring methods are essential for electrical safety. Wiring methods refer to the way electrical conductors are installed and protected. The NEC specifies the types of wiring methods that are permitted for different applications. Some common wiring methods include non-metallic sheath cable, or NM cable, rigid metal conduit, or RMC, intermediate metal conduit, or IMC, electrical metallic tubing, or IMT, and flexible metal conduit, or FMC. NM cable, also known as ROMIX, is a type of cable that consists of two or more insulated conductors enclosed in a non-metallic sheath. NM cable is commonly used for residential wiring. RMC is a type of rigid steel conduit that provides excellent protection for electrical conductors. RMC is typically used in industrial and commercial applications. IMC is a type of steel conduit that is lighter than RMC but still provides good protection for electrical conductors. IMC is often used in commercial and industrial applications. EMT, also known as thin wall conduit, is a type of steel conduit that is lighter than IMC. EMT is commonly used in commercial and residential applications. FMC is a type of flexible metal conduit that is used to protect electrical conductors in locations where flexibility is required. FMC is often used to connect motors and other equipment that vibrate. The NEC specifies the requirements for installing each type of wiring method. These requirements include the size of the conduit or cable, the spacing of supports, and the methods for making connections. It is important to follow the NEC requirements for wiring methods to ensure the safety and reliability of electrical systems. Electrical panels are the heart of an electrical system. The electrical panels distribute power from the service entrance to the various circuits in the building. Electrical panels contain circuit breakers or fuses which protect the circuits from overloads and short circuits. Electrical panels must be properly sized to accommodate the electrical load of the building. The NEC specifies the requirements for sizing electrical panels. Electrical panels must be installed in a location that is accessible and free from obstructions. Electrical panels must be properly grounded and bonded to ensure the safety of people and equipment. Electrical panels must be labeled to identify the circuits they serve. It is important to follow the NEC requirements for electrical panels to ensure the safety and reliability of electrical systems. Electrical boxes are used to enclose and protect electrical connections. Electrical boxes are available in a variety of sizes and shapes to accommodate different types of wiring and devices. Electrical boxes must be made of metal or plastic and must be listed by a recognized testing laboratory. Electrical boxes must be properly grounded and bonded to ensure the safety of people and equipment. Electrical boxes must be securely mounted to a wall, ceiling, or other structure. Electrical boxes must be sized to accommodate the number and size of conductors and devices that will be installed in them. The NEC specifies the requirements for installing electrical boxes. It is important to follow the NEC requirements for electrical boxes to ensure the safety and reliability of electrical systems. Electrical permits are required for many types of electrical work. Electrical permits are issued by local building departments and are required to ensure that electrical work is performed safely and in accordance with the NEC and local codes. Electrical permits typically require the submission of plans and specifications for the electrical work. Electrical permits also require inspections of the electrical work to ensure that it is in compliance with the code. It is important to obtain the required electrical permits before starting any electrical work. Failure to obtain the required permits can result in fines and delays. Electrical inspections are performed by local building departments to ensure that electrical work is performed safely and in accordance with the NEC and local codes. Electrical inspections are typically required at various stages of the electrical work, such as after the rough wiring is installed and after the final connections are made. Electrical inspectors will check to ensure that the electrical work is in compliance with the code and that it is safe for use. If the electrical work fails the inspection, the inspector will issue a list of corrections that must be made before the work can be approved. It is important to cooperate with the electrical inspector and make any necessary corrections promptly. Electrical safety training is essential for anyone who works with electricity. Electrical safety training teaches workers how to identify electrical hazards and how to work safely around electricity. Electrical safety training typically covers topics such as electrical shock hazards, arc flash hazards, lockout-tagout procedures, and the proper use of personal protective equipment. Electrical safety training should be provided by a qualified instructor and should be updated regularly. Electrical safety training can help prevent electrical accidents and injuries. Working with electricity can be dangerous, but by following safe work practices and using appropriate safety equipment can minimize the risks. Always to energize electrical circuits before working on them, and use lockout-tagout procedures to prevent accidental energization. Wear personal protective equipment such as safety glasses, gloves, and insulated footwear. Use insulated tools to minimize the risk of electric shock. Maintain a safe working distance from energized equipment and be aware of the potential for arc flash. Regularly inspect electrical equipment for signs of damage or wear, and repair or replace any defective equipment promptly. Never bypass or disable safety devices such as circuit breakers and ground fault circuit interrupters, or GFCIs. By following these safety tips can help prevent electrical hazards and ensure a safe working environment. Always follow safe practices when working with electricity, such as wearing appropriate personal protective equipment and using insulated tools. Never work on live circuits unless absolutely necessary, and always follow lockout tagout procedures to de-energize circuits before beginning any work.